video is on electrophilic aromatic substitution, and in general this is going to be just the basics. We'll talk about reactions in another video. So in this I'll often abbreviate it as EAS for electrophilic aromatic substitution, and so just to give you an overview of the complete reaction, what we're doing is we're going to end up substituting an electrophile for a hydrogen on the aromatic ring. And so you can see that the general process for the reaction involves the electrons from the aromatic ring attacking some electrophile. And when this happens, you are going to then essentially form a carbocation on the ring. Now, you can imagine that this is the rate determining step of a reaction, or this reaction type, because we're having to initially break aromaticity to begin the reaction. So now you can see that we have a carbocation, and this carbocation is stabilized because you can see that it is secondary, but also it's secondary allylic. And so we have this carbocation intermediate that allows for us to follow the process of this reaction. We can move the carbocation all the way around the ring. Now I'm just going to write here for the next step of the reaction, the fast step, as a base, but when you get into the reactions you can see that it will be many different things for the B- that is there. And this step is the formation at this point, or regeneration of aromaticity. Once this happens, you can see that now you have substituted the hydrogen that was there on the ring. You've gotten rid of it using the B- or the conjugate base of an acid, whatever it may be that you use, and you have placed on the electrophile. So why does it undergo this type of reaction, and why do we form this carbocation here? Well, first of all, this carbocation, as was mentioned, is stabilized by resonance. So if you notice, here we can draw an aromatic ring, and you can see that if I add this electrophile to it now, and as I mentioned above, we're going to generate a secondary carbocation that is allylic. So here is our rate determining step of this reaction, and we have now our secondary allylic carbocation. And as I said earlier, you can move this carbocation throughout the entire ring. So we can draw several different resonance structures here, whereby we move the charge, the positive charge, by virtue of moving the electrons in the ring. We move this charge all the way around the ring into different spots. So again, if you can move a charge, you should often think of a charge as a hot potato, and if you hold a hot potato, if you hold it in your hand by yourself, you're likely to get burned. However, if you can toss it to someone else, you're less likely to get burned. And if you can toss that potato to multiple different people before it gets back to you, the chances of you getting burned are much less. And the same holds true with charges. So if we can move this charge around the ring, as you can see that I'm doing, you'll note here that we have an increased amount of stability. Now, why, for electrophilic aromatic substitution, do we not just get some addition product? Well, it turns out that if we were to undergo an addition reaction, we wouldn't end up reforming the aromatic system. So this substitution reaction allows us to regenerate our aromatic ring and gives us a very stable end product. Okay, so let's look at some factors that affect our substitution reaction here. So factors that affect the ring and the behavior of the ring. So we can essentially increase or decrease the reactivity of our aromatic ring based on the substituents that are there. So these are what we refer to as electronic effects. Now you can also have steric effects, and that will be handled later, but mostly for this video we're just going to focus on the electronic effects. And so we have two major effects. One of them is the inductive effect. So inductive effects are essentially due to difference in electronegativity of atoms that are connected through a sigma bond. So those things that are connected to electronegative elements, they're going to be deficient in electrons because the electronegative element is going to pull the electron density away from it. So you can see an example here. If we add fluorines to a carbon that is adjacent or attached to our ring, you can note that inductively these fluorines are going to pull the electron density away from the carbon there, putting a partial positive charge on the carbon. Now, I should mention at this point that there are a couple of factors that you need to remember regarding inductive effects, and those are the fact that they are additive. In other words, having 3 fluorines here is more effective than just having 1. The effect is stronger. The second tidbit about inductive effects is that they are distance dependent. So if the 3 fluorines were, say, 2 more carbons away, then their effect on the ring would be essentially minimal. So distance is extremely important as well. So again, when we have the inductive effect, we're looking at no essential movement of electrons through a pi system, but we're inductively pulling electrons through a sigma bond. And what this does in this case, as our example, this is deactivating the ring because we're pulling electron density out of the ring, and therefore it can't attack that electrophile that we would have. The next type of effect that affects substitution is resonance, or the next electronic effect that deals with substitution is resonance. And so this is now when we actually get into moving the electrons. Physical movement of electrons through a pi system is what we refer to as resonance. So as an example, I'll put on an electron withdrawing group here on an aromatic ring. So we have a carbonyl compound here, and you can see that what we can do is we can actually take the electrons from the aromatic ring and move them onto this carbonyl. This then pulls the electrons outside of the ring. The ring no longer has full amounts of electrons, and now we'll end up with a positive charge on it. So you can see that we have indeed this positive charge that's on the ring. If there is a positive charge on the ring, then that means that you don't have sufficient electron density to really attack anything else. You're pulling those electrons out of the ring. And we can continue to move these electrons just like we did previously. We can move this around the ring here to further stabilize the charge that we have. Don't want to forget a methyl group there. And so we can move this guy all the way around the ring. Now you can see that it's in the para position or the 1,4 position. And then we can make it move one more time by moving this over to the ortho position or the 1,2 position there. So this is electron withdrawal by resonance. Now this leads us to another aspect of electrophilic aromatic substitution, and that's when you're determining what effect is the greatest. And so here we have to consider the fact that when you have possibly both resonance and inductive effects, which one do you choose? Which one will dictate whether or not your ring will have electron density versus whether it won't have electron density. So you should remember that resonance is the stronger effect, and so when you can have resonance will win. As an example, we can look at phenol. So here is phenol, and what you can see is that oxygen, if you were to look on the periodic table, is fairly electronegative. It's to the right, farther to the right of carbon, and we have actually a dipole between the carbon there on the ring and the oxygen. So inductively, in this case, we have an inductive withdrawal of electrons. But what's not being shown in this is that we also have on the oxygen lone pairs. And this brings us to another aspect of phenol, which is resonance donation. So we can use those lone pairs to push electrons onto our aromatic ring. So here I have phenol that I'm drawing again, and we have these lone pairs. Now you can take these lone pairs and you can actually push them onto the ring like so, which then forces an extra set of electrons onto the ring, which gives the ring an overall negative charge. And then we can continue to move this charge all the way around the ring here, just like so. And you can see that in this case, every time that I'm moving this charge around, what you can see is that in the first one, the negative charge is on the ortho position, and in this one, the negative charge is now on the para, or the 1,4 position, like the number 4 position there. And then I'm going to move it again, and this is going to push this negative charge back to the ortho position, which is position number 2 on the ring, right? Or it is 1, 2 from the initial, substituent there. Now also remember that you keep up with your charges, maintain the formal charges of everything that you have on the ring. Now I'd like for you to note that where the position of these charges is important for how things are directed. So in this case, or in most cases, resonance will win. It is the stronger effect. So this brings us finally, which I briefly mentioned, regarding the position of those charges. This brings us to what we call directing effects. So what substituent that you may already have on the ring, and if you go to do a reaction to put something else on the ring, then those substituents play a role in whether or not the ring A is going to be activated, and also where that next substituent will go. So groups that activate the ring, right, either inductively or through resonance, will put other substituents that you're adding or direct them to the either ortho and or para position. So remember, ortho is the number 2 position from the initial substrate, para would be the number 4 position, right? So groups that activate direct into these either 1, 4 or they direct 1, 2. Now, as an example, we can draw aniline here. And I've got the lone pairs there on this nitrogen. And note, just like before, now what I'm going to do is I'm going to push these electrons onto this aromatic ring. Notice that we have in each case the negative charge, just like in the previous example, is going to be on the ortho position here. So this next resonance structure will have the negative charge in the ortho position. And then if I continue to move this around, you'll see that the next spot with the negative charge will now be in the para position, or the number 4 position. And then finally I'm going to move the charges one more time, and what you can see is that the charges are now going to be in the ortho position. So in every case, wherever we move these charges, the concentration of electron density that we have on the ring due to this movement of electrons is on either the ortho or para position. And so this is why groups that are donating, right, either through inductive or resonance, will add ortho and para. Let's look at the opposite. So let's put an electron withdrawing group on there. So groups that withdraw electrons deactivate the rings. In other words, they take density away from the ring and they make it harder for the ring to use its electrons to attack an electrophile. And this again is either inductively or through resonance. And what these groups do is direct to the meta position, so the 3 position on the aromatic ring. As an example, let's look at nitrobenzene. So here is nitrobenzene, and what you're going to see is that when I take the electrons out from this and move them onto the nitro group, you're now going to see a positive charge that's going to develop in the ortho position here. So there's my positive charge, and we can move this further around again just like before, so we can continually move this around the ring. And note that now when we move this, and I forgot the charge there on the nitrogen, notice that when we move this guy around, that in each instance the charge, the positive charge, is on the ortho and para positions in the ring. So the only place that has electron density is the meta position. So for this reason, electron withdrawing groups direct meta.